Problem statement. Determine the force in the x direction Fx of the water on the horizontal bifurcation shown in the figure below. If the pressure P1 is 225 kilopascals. Neglect head losses. Okay, so the pressure P1 is 225 kilopascals. The problem says that this is a horizontal bifurcation, which means that the elevation of the three pipes are the same, so they are on a horizontal plane. And the question in this problem is find the force in the x direction. Okay, so the question is find the force in the x direction of the water on the horizontal bifurcation. So the question is find the force of the water on the bifurcation. I'm going to call F. Okay. So whenever we have a problem of forces, we have to apply the momentum equation. Here we have three pipes, so we have to apply the general equation uh, of the momentum for steady flows. And the general equation of momentum for steady flows is sum of forces is equal to the sum of elements 1 to n. In this case, we have three pipes, density I, area I, velocity I, and the dot product of the velocity times the unitary vector. We know the unitary vector is always pointing outwards in the control volume. So this is going to be N2, this is going to be N1, and this is going to be N3. Okay. Of course, here our control volume is going to be something like this. Control volume is going to encompass the three pipes. It's going to be more or less like this. So that will be the control volume. Okay. So we can write this general equation of momentum in the following form. So because we are interested in the force in the x direction, so this is our x direction, we can say, okay, sum of forces in x will be equal to, so we can start with pipe 1. For pipe 1, we are going to have a density 1. It's going to be area 1. The velocity 1 is going to be velocity in 1 positive because the x direction is to the right. And then we have the product of velocity 1 times the unitary vector. So velocity 1 is pointing to the right and n is pointing to the left. So therefore that the product is going to be negative because the angle is 180 degrees. Okay, so this is going to be minus V1. Then for pipe 2, this is going to be 0 because the velocity component of pipe 2 in the x direction is 0. Now for pipe 3 has, by the way, this is pipe 1, pipe 2, and pipe 3. It seems the figure is not showing clearly, but those are pipe 1, 2, and 3. So for pipe 3, we have a component in the x and the y direction. So we can say this is the example, the y direction, and we have the component also in the y direction, but the question here is in the x direction. So if this angle is 45 degrees, this is the velocity 3, so this is going to be velocity 3 cosine of 45 degrees, and this will be velocity 3 sine of 45 degrees. Okay, so it's going to be plus density 3, area 3. The component of the velocity in the x direction is going to be velocity 3 sine of 45 degrees, positive, right? Because this is the component and this is pointing in the positive x direction. So that will be velocity 3 sine of 45 degrees. And the product of B3 times the unitary vector in 3 is going to be, sorry, the velocity 3, which is here, times n3 is going to be positive. And the reason is because velocity 3 and n3, they are pointing in the same direction. The angle is going to be 0. So the product is going to be velocity 3. Okay, so that's going to be what we have. And now we also have to find the external forces, right? The external forces we can determine in the following manner. So here we have a pressure P1. Here, let's see, we have a pressure P1, which is 225 kilopascals. So that's the pressure uh, at that control surface. Therefore, the force. So we have to ask ourselves what this water is doing to my control surface. Basically, is pushing pushing with a force F1. Okay. What about here? We also have a force F2 here, and here we have a force F3. F2 and F3 will be equal to 0. And the reason is because the pressure in 2 and the pressure in 3 are equal to 0. They are atmospheric pressure. So if the pressure are equal to 0, the force is also going to be 0. However, F1 will be equal to pressure 1 times area 1, and pressure 1 will be equal to 225 kilopascals. Okay, so we can write this then in the following manner. Sum of forces in x, so F1 is going to be positive because it's in the x direction, in the positive x direction. So it's going to be F1 positive. Okay, and then we have nothing else because F2 and F3 are all 0. Then we have to ask ourselves what the um, reaction of the pipe is towards the control volume. So the control volume is the water, right? So the pipe that is enclosing the control volume is doing something to my control volume. So we can say, let's assume that the control volume is trying to move to the right, and therefore we can say, okay, the pipe is trying to hold, is trying to react to the pushing of the water. So the reaction would be to the left, right? So if that's the case, we can say, okay, the force, the reaction of the pipe to the control volume could be to the left. We can assume that the water is trying to push to the right, and the reaction of the pipe will be, of course, to the left. So if that's the case, the force F will be negative because it's pointing towards the negative x direction. So it's going to be F1 minus F. That will be equal to, so it's going to be minus density 1, area 1, velocity 1 square, plus density 3, area 3, sine of 45 degrees, velocity 3 square. That is what we have. This will be my equation 1 that results from the momentum equation. Okay. We know F1. F1 is going to be 225,000 pascals times the area 1. So I know F1. However, we are missing to get F, we need to get the velocity 1 and velocity in 3. Density 1 and density 3 are the same and they are equal to the density of the water. So what I am missing right now is the velocity 1 and the velocity in 3. So to do that, we can, um, uh, for instance, apply the continuity equation. We can start with the continuity equation. So we can apply here continuity. And continuity tells me that the flow coming in has to be equal to the flow going out. So in this case, the flow coming in is in pipe 1, the flow is coming in, and in pipe 2 and in pipe 3, they are going out. So we can say the flowing 1 has to be equal to the flowing 2 plus the flow in 3. The flowing 1 is area times velocity 1. Area is pi times 0.12 squared divided by 4 times velocity 1, and this will be equal to the flowing 2, which is a pi times 0.06 squared divided by 4 times velocity 2 and plus area 3, which also has a diameter of 6 centimeters, which is going to be pi times 0.06 squared divided by 4 times velocity 3. Okay, so we can simplify pi's and 4's in both sides. 0.12 is twice 0.06. So we can simplify that. So here we can say this is going to be 4 velocity 1 is equal to velocity 2 plus velocity 3. I am doing this because 0.12 is twice 0.06. So to the square will be 4. And I can factor the 0.06 everywhere. Okay, so I have a 4 times velocity 1 is equal to velocity 2 plus velocity 3. So that will be my equation 2. Now, one condition of the problem is neglect head losses. So that is telling me or inviting me to apply the Bernoulli equation or the energy equation. In this case, I can apply, example, the Bernoulli equation. And I can apply Bernoulli equation here, example, between 1 and 2, or 1 and 3, or 2 and 3. Okay, but uh, I can apply at least two Bernoulli equations here, between 1 and 3 example, and between 2 and 3. Okay. Why I am doing that? Because I want to find the relationship between what are the relationship between the velocities and pressures between those sections. Okay, so I'm going to apply Bernoulli equation, and we can start example with uh, points 2 and 3. Okay, so if we do that, I have a pressure in 2, at outlet of 2, gamma plus velocity 2 squared 2g plus theta 2 is equal to pressure in 3 gamma plus velocity in 3 squared 2g and plus the elevation uh, of 3. The elevation of 2 will be equal to the elevation of 3, and the reason is because we have a horizontal system. So the level or the elevation of the pipes are the same. Also, the pressure in 2 is equal to the pressure in 3 because both of them are open to the atmosphere. So they will cancel. So from this, we can say that velocity in 2 will be equal to the velocity in 3. The velocity will be the same. Velocity in 2 is equal to velocity in 3. Okay, so from this, we can say, we have equation 2 that tells me that 4 times velocity 1 is equal b2 plus b3. So if b2 and b3 are the same, we can say, okay, for velocity 1 will be equal to 2 times velocity 2. And from this, velocity 2 will be equal to 2 times velocity 1. So that's going to be my modified equation. So velocity in 2 will be twice the velocity in 1. Okay, but this still doesn't give me the velocity in 1 and velocity in 2. I need one more equation that helps me to find B1 and B2. But here you guys can notice that the pressure in 1 is 225 kilopascals, and I haven't used that information yet. So I can apply Bernoulli between 1 and example 2 or 3. Okay, so since we know the information here in 2, let's apply Bernoulli between 1 and 2. Okay, so we can say I'm going to apply now Bernoulli between 1 and 2. So that will give me a pressure in 1 gamma plus velocity 1 square 2g plus theta 1. This will be equal to pressure in 2 gamma plus velocity 2 square 2g and plus the elevation in 2. So the elevation in 1 and elevation in 2, they will cancel because we mentioned that this is a horizontal system. So the elevations of the pipes are the same. Pressure in 2 is equal to atmospheric, so this will be 0. And the pressure in 1 is 225 kilopascals, so it means 225,000 pascals. And the value of gamma is 9,800 or 9,810, they're pretty much the same. And then here we have a plus velocity 1 squared divided by 2 times gravity, 9.8. And this is equal to velocity in 2. And velocity in 2 is equal 2 times velocity 1, which means that this is going to be 4 times velocity 1 squared divided by 2 times 9.8. So from this, the only unknown is velocity 1, so we can get a value of velocity 1 here. And the value of velocity 1 from this is going to be 12.25 meters per second. And therefore, velocity in 2 will be twice of this. So that will be 24.5 meters per second. And of course, velocity 3 also will be equal to 24.5 meters per second. Okay, so I think pretty much we are done. Now we have to go back to equation 1. So we can go back to in 1 and we can substitute values. So in 1, we have a F1 times area. So F1 is pressure times area. So the pressure is 225,000 pascals. So 225,000 pascals times the area, and the area is pi times 0.12 squared divided by 4 minus F, and um, that will be equal to minus density 1, so it's going to be minus 1000. Area 1 is going to be pi times 0.12 squared divided by 4 times velocity 1 squared. So velocity 1 is 1225 squared. Okay. And then we have plus density 3, area 3. So we have a plus density is going to be 1000. Area is pi times 0.06 squared divided by 4 times sine of 45 degrees and times velocity 3 square. So velocity 3 is 24.5 square. Yes. So we will have that one. Let me check. So it's going to be 1000 pi 0.06 square for 24.5 square sine of 45 degrees. Okay, this looks correct. And therefore, from this, the only unknown is f, and f will give us a value of 3041.8 newtons. Okay, so we should mention that the value of f is positive. The value of f is positive. So this means that the direction of the reaction we have assumed is correct. So f, the reaction of the pipe towards the control volume, is to the left. But the question here is determine the force of the water on the horizontal bifurcation. So the reaction is to the left, but the water is acting to the right. So the water is pressing the pipe to the right, and the pipe is reacting to the left. Okay, so then we can say the force of the water on the bifurcation is going to be 3041.8 newtons, and the direction is going to be to the right. Okay, so the force of the water on the pipe is to the right, but the reaction is to the left. Okay, but the question is now the force of the water, so it has to be to the right. That is the answer.